Welcome back everyone. Today we learn about lenses. A pair of glasses contain lenses to allow people to see better at far distances. But what are lenses? A lens is a transparent material with a curved, spherical surface. Transparent materials like water, clear glass, or plastics can be used to make lenses. Let us discover the different terms in this topic. First, let us start off with the principal axis. Observe the diagram below. We call this line the principal axis, an imaginary line drawn symmetrically through the optical center of the lens and is perpendicular to the surface of the lens. Next we have the optical center. The optical center is a point whereby light rays will pass through and not deviate or bend in another direction. Hence, when a light ray of any direction passes through this point, it will continue to move in that direction. We also have the principal focus, which is a point when parallel rays of light converge to the single point along the principal axis. Now that we know about the principal focus and optical center, let us talk about the distance between the optical center and principal focus. This distance is also known as the focal length, which uses the symbol f. Now, when we place an object on one side of the screen, there will be an image on the other side of the screen. The object distance, labeled as u, is defined as the distance from the optical center to the object. Image distance, v, is defined as the distance from the optical center to the screen. Here is an equation relating object and image distance. F in this equation refers to the focal length of the lens. There are three ways we can physically find the focal length. Firstly, we can shine an illuminated object on a screen as shown below. The position of the screen where the image is the clearest will be the focal length of the object. The next accurate method is to measure the object distance, image distance, object height, and image height, and then we use the data to plot a ray diagram to find the focal length. Lastly, we can use the most accurate method, which is finding different values of object distance and their corresponding values of image distance and plot a graph that represents the equation 1 over u plus 1 over v equals 1 over f. For the third method, what this means is that we can create a linear graph and find the focal length from there. How? We use the equation shown. This can be rearranged to either equation as shown. From both equations, if we plot a graph accordingly to either equation, it will give us a y-intercept of 1 over f. Another concept that we also talk about in this topic is the linear magnification, which is also known as the ratio between the lengths of the image and the object. We can either take the ratio of their widths or their heights. There are two types of lenses, converging and diverging. Take a look at the diagram. When parallel light rays meet, the light rays concentrate to a point known as the principal focus. Converging or convex lenses cause light rays to converge after passing through the lens. In such cases, they are normally thicker in the middle than at the edges. Here are three such examples: the double convex, plano-convex, and the convex meniscus. In a converging lens, the focal length depends on the thickness of the lens. A thicker lens suggests that it has a shorter focal length, while a thinner lens suggests that it has a longer focal length. The diverging lens, however, is different. Diverging lenses causes light rays to diverge after passing through the lens. A diverging lens is normally thinner in the middle than at the edges. Such examples include the negative meniscus, plano-concave, and the biconcave. Now, let us introduce ray diagrams. Ray diagrams allow us to see how light interacts with the lens. But in order to draw them, there are a few things we have to take note of. When parallel light rays that are parallel to the principal axis pass through the lens, the light ray will focus at a point F. The plane perpendicular to the principal axis, and consists of point F, is known as the focal plane of the lens. Next, parallel light rays not parallel to the principal axis will focus at F' and not F. The focal plane consists of both point F, the point on the principal axis which is a focal length away from the optical center, and the point F', the point where all the light rays will converge to. Let us look at the diagram again. Do you notice something strange? There is a light ray that remains undeviated. This is because this particular light ray passes through the optical center, and hence will not deviate, but still focus towards the point F'. Take note, unlike the first two properties, this particular property is true for both converging and diverging lenses. When we draw ray diagrams, typically the main goals will be related to the property of the image formed. When describing the image formed, we have to take note of four traits of the image: the size compared to the object, the position of the image, whether the image is inverted or upright, as in if the image turns upside down or not, and whether the image is real or virtual, as in whether the image is on opposite sides or the same side as the object. Now, how do we draw a ray diagram? When we draw a ray diagram, we have 3 steps to follow as shown. Let's draw it together. We are given an object that is placed far behind the focal point. What should we start with first? First, draw a ray intersecting the optical center, which remains undeviated and hence, it is a straight line through the optical center. Next, we draw a ray parallel to the principal axis. Recall that the light ray parallel to the principal axis will converge to the principal focus. Hence we will draw the light ray such that it directs to the principal focus as shown. This results in the light ray to be drawn as shown. Lastly, we need to draw the image. The image is located at the intersection of the 2 rays. This is the final drawing of the ray diagram. Here we have a ray diagram of a diverging lens. You will not be required to know how to draw a diverging lens, but you are required to know that when parallel light rays pass through the lens, the light rays will be diverged as shown in the ray diagram, where the lines of the light rays converge behind the lens. As a result, with the diagram shown, this results in the image formed to be virtual, upright, and diminished. By using the ray diagrams, we can use this to determine what the images will look like depending on the position of the objects. You will be required to learn how to draw these ray diagrams. Firstly, let us talk about far-distance objects. For far-distance objects, we assume that the light rays are parallel to each other. Try to draw out the ray diagram. Did you get this diagram? From this diagram, we can say the image will be formed at the focal length. The image is real, diminished, and laterally inverted. One example is the telescope, where we see far-away planets from a very large distance. Now, let us continue to draw more diagrams. Here, the object is more than 2 focal lengths away from the optical center. Attempt to draw the ray diagram for the scenario. We will end up with this diagram. The image is located between F and 2F. It is real, diminished, and laterally inverted. One such example of this ray diagram is a camera. Now, let us continue to draw more diagrams. Here, the object is exactly 2 focal lengths away from the optical center. What will the ray diagram look like? Pause here and try to draw it out. We will end up with this diagram. The image is located at 2F. It is real and laterally inverted, but has the same size as the object. One such example of this ray diagram is a photocopier, where the size of the image is the same as that of the object. Next, the object is placed somewhere between 1 to 2 focal lengths. What would the ray diagram look like? Pause here to try it out. Here is the ray diagram as shown. From the diagram, the image formed is beyond 2F, the image is real, magnified, and laterally inverted. An example for this scenario is a screen projector. Next, the object is a focal distance from the optical center. The image is formed at infinity and it is located on the same side as the object. In fact, the image is upright, virtual, and magnified. One such example includes overhead lights in cars. Lastly, we have the object being less than a focal length away from the optical center. Try drawing the ray diagram. This is a tricky ray diagram because if you notice, the light rays do not meet as shown. However, we can still get the image. How? Just like the ray diagram for an object at a focal length away, and the ray diagram for a diverging lens, we can extend the light rays towards the left. This results in the image being formed on the same side as the object, suggesting it is virtual. The image formed is magnified and upright, meaning it does not laterally invert. It is important to note the lines drawn to determine the position of the virtual image is dotted. Dotted lines are used to label the virtual image, instead of using full lines. One example is the magnifying glass. Here is a table which summarizes what we have done so far. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.